He makes fun of the political leaders, presidential, completely crap, but gives speeches about putting. I think know that keep hearing it for identification.
Yeah, that sounds local.
I guess he's not running this year, unfortunately. I would agree with that.
That's what I'm talking
I'll think about it. No. So a division problem with complex numbers is an interesting sort of endeavor. This will be the hardest of the complex number things that we've talked about so far. Adding, subtracting, easy. Multiplying, pretty easy. Plotting, like third grade easy. Modulus from yesterday, yeah, pretty easy, right? There's a lot of meat on this bone here. So really the goal is, it's weird to say this, but instead of really thinking of it as I'm dividing two complex numbers, we kind of want to think of it as I'm fixing the fraction. That's kind of over the years what I've decided is it just never really feels like an actual division problem. It feels more like fixing a fraction. So one of the rules in math that you probably don't yet know is that you're not allowed to have anything square rooty in the bottom of a fraction. I don't know if you were aware of that. What we try to do is always keep the bottom of any fraction from being irrational. So I'm going to show you something that you may want to not write down because it might look when you look back on your notes like what was Mr. Ahern talking about. But if you ever got to a point where you had like 4 over the square root of 3, and we will talk more about this, but not today. There's a problem with that in that there's a square root in the bottom, and it's just a thing in math that's not something we do. So what we're going to do is called rationalizing the denominator. So what math people do is they say, well, I can't just erase the square root of 3, like that's cheating. But what I can do is multiply it by something that makes it not be a square root anymore, right? And you know this much about roots, that if you multiply a root of 3 by another root of 3, you just get 3, right? Any square root times himself just becomes what was inside. And then you multiply the top by the same thing, and you wind up on top with 4 roots of 3, but on bottom 3. So these two purple boxes are identical, but the one on the right is the one that we would accept as done because it doesn't have a root. So that's an idea that we need to keep in our minds as we go through today, is that you're just not allowed to have roots in the bottoms of fractions. So in the white fraction division problem that you see, is there a root in the bottom? Yes, there is. There is. You don't see it, but there's one. Who is it? It's I. What is I? I haven't heard it yet. What is I? It's not -1.
-1.
Thank you, Seth. Finally, there it is. Remember that I is equal to the square root of -1. I can't leave that down there. So as I go through today's lesson, just bear in mind when you ask yourself, why are we doing this? Well, we're doing it because really we just can't leave the bottom of it. So these division problems really boil down more to just let's fix it. We're going to do something called rationalizing the denominator here. You don't need to know that, but that's technically what we're up to. So let's begin. So several days ago, I taught you how to multiply complex numbers. And you might remember that there are some pretty significantly special cases. Like if I had 3 plus 4i and I multiplied it by 3 minus 4i. Do you guys remember what those are called? Starts with a C? Or complex something. Good guess. That was excellent. You had the first 4 letters right. They're called complex conjugates. And when you multiply complex conjugates, do you remember what significant event occurs? They do. You wind up with a real number. And this is critical. So if this next 2 minutes doesn't make sense, don't let me go on, because the rest of the lesson will just get worse if this doesn't. So stay with me and make sure you're good. So when I multiply these together, remember all I have to do is 3 times 3 is 9. And 4 times 4 is 16, and then I add those together, and the answer is 25. And the reason you'll remember for that is like Corbin said, because when I multiply these two, what do I get? And when I multiply 12i, right? And when I multiply these two, what do I get? And because they're complex conjugates, that pattern will literally always exist, that the two middle ones and the two outside ones are going to be cancelers. And so all we ever have to worry about is the first two, 9. And the back two, remember, would have been minus 16i squared, of course, but then we've been down this road, it becomes plus 16. So let's practice for a few minutes multiplying by conjugates. What if I gave you -1 minus 3i? What's his conjugate? -1 plus 3i. Good. You don't change the number in front. You only change the verb in the middle. The plus becomes a minus or the minus becomes a plus. And because they're conjugates, the work is really quick. What is -1 times -1?
1.
And what is 3 times 3? And what is 1? It's not negative. It's never going to be negative because, and I can say this, will one of these yellow circles always be positive and one always be negative? Will a negative times a positive always be a negative? And will there always be an I squared? So if we can say always, 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 a negative with an I squared attached to it always becomes a what? And I say always. I don't take that word lightly. So it will always be an addition problem. 1 plus 9 is very simply put 10. Right? So look what we did. We took a complex number and we made it a real number, just like that. Let's do it again. Let's do -2 plus 7i. What is his conjugate? So what we're doing here is through sheer wizardry, like Harry Potter, black magic-y kind of stuff, is we're taking complex numbers and making them real numbers. And so when we multiply these conjugates, this should not take anyone longer than like 3 or 4 seconds. What's 2 times 2?
4.
What's 7 times 7?
4.
What's 4 plus 49? 53. We don't burden ourselves with the thoughts of the negatives. We just always understand that there's no way around it being a positive plus a positive. We good? Having said that, let's go back to our problem here. And if we understand our mission, and our mission, remember, is to make the bottom not have that stupid I, we now understand that we can create a conjugate. And we can multiply the top and the bottom of the fraction by that conjugate, right? You could do whatever you want to a fraction as long as you do the same thing to the top, to the bottom. You can multiply the top by 54. Just do it to the bottom, and everything's fair. So first thing I'm going to do is I'm going to put some parentheses around both of these because now it's going to become a multiplication situation. And we are going to multiply the top and the bottom by the conjugate of the bottom. What's the conjugate of the bottom? Nice job, guys. 6 minus 9i. Same on the top. And the bottom, through practice and practice and practice, we get to a point where we just don't have to slow down as much, right? What is 6 times 6? What's 9 times 9? What's 36 plus 81? 117. Okay, so what we have right now is on the bottom, we have 117. Everybody with me? You sure we're good? Okay, now this part, there's really no workaround. The bottom, I feel like we can bypass and shortcut pretty quick. The top is what it is. So the top is the part where you just gotta go for it. So here we go. 4 steps. What is 4 times 6? What is 4 times -9i? -36i. And what is 5i times 6? So plus 30i. And at the back end, what is 5i times -9i? So let's just put plus 45, right? Because yeah, you're not wrong if you say -45i squared, but again, that I squared is always just going to change signs. So it's more efficient to just put the plus 45. So when I add the 24 and the 45 in the front end, I wind up with, so I have 69 minus 6i over 117. And then the final step in this process is that all answers need to be written in standard complex form, which remember is a busted up broken A plus BI. So all you simply have to do, follow my arrows if you'd be so gracious. Your A is going to come from this direction right here. And that's going to be the number 69 over 117. And then the BI is going to come from the direction of the green arrow, which is going to be minus 6/117ths of I. We're not quite done, but be it known that oftentimes that will be the end of the problem. Because now we've done it. We made a plus bi. A is 69 1/17. B is negative 6 117. Does anyone know why this isn't done? No, you cannot add those fractions together. They are not like terms. That's like, Tristan, that's like saying that 3 minus 4x is equal to negative 1x. This one has an I. These are not like terms. You cannot put them together. There's something else, though, that we might be overlooking. What is it? You can reduce both fractions down. I believe they're all divisible by 3. So just look independently at each fraction. Look at these numbers. If you divide the top and the bottom both by 3, you're going to wind up with 23 over, I think, 39. Check my math, but that feels pretty good. 90, 20, yeah, that's good. And then the second fraction, I'll put a purple box around it. Those can also both be divided by 3, which results in minus 2/39 of I. This is what a proper final answer should look like. A plus BI. Okay. So that's the process. Let's do it again. Let's do 5 minus 7i over negative 1 minus 4i. This will take way less time because last time I wanted to go on the side journey and explain to you kind of the logic. This time you get it. We're trying to fix the bottom. So what do? You guys are a quick study. Good job. So we're going to put on parentheses to indicate, like, watch out, everyone, incoming multiplication. Put a time sign, make a fraction, and you nailed it, guys. So we're going to multiply the top and the bottom by the conjugate, which is negative 1 plus 4i. The bottom should be quick. If it's you find yourself that the bottom is a struggle, you need to come see me, like, just straight away, immediately, because the bottom should be just like a gift. What's the bottom going to be? 17 for sure. 1 plus 16 is 17. And now as we work our way across the top, let's try to be more efficient mathematicians this time. And to be efficient, follow these purple connectors and stay with me on this ride and let me know if it doesn't make sense. I'm going to multiply these purple connectors, and they wind up being like terms. I hope you agree. So the first purple connector makes what? Negative 5. So hold on to that. Negative 5. Now look at the second pair, the purple pair. What do they make? They don't make negative 28. They make positive 28 because it would have been negative 28, but it has an I squared stuck on its butt, right? And a negative 28 with an I squared really becomes a plus 28. So I can kind of hold on to this as I go and make myself a quicker mather, right? So I started with negative 5 and I'm adding 28. And what's negative 5 plus 28? It is 23 all day long. Just trying to make it so maybe you could show a little bit less work. And then depending on your level of bravery, you can also do this yellow one and this green one mentally as well. I got no issues if you want to. The two yellow ones make 7i. The ones on the outside make 20i. So if you take your 7i and your 20i and you add them up, what do you get? Yeah, we can be quicker. If you want to show all 4 steps, I'm never going to get in the way of that. And do we like that answer? It's not done, right? It's not in standard complex form yet. So we want to break it. And the divvying just comes from building a couple of fractions. There's this fraction, and then there's always going to be this fraction, and they're just going to be your A and B. We want to break them so we get one complex number, not a complex number divided by 17. So the final answer would be 23/17 plus 27/17 of I. Make sure that that I gets off to the side, not on the top, not on the bottom, of course, but just off to the side. Okay, 2 more. That went a little quicker that time. That one should have felt better. Hopefully this one feels even better. We're going to do negative 9 plus 3i divided by negative 8 plus 4i. Would you guys like to try it? And I'll give you a couple of minutes. All right, let me pause the recording and then I'll let you try and then we'll talk answers here. Because I forgot to resume, I'm going to scroll back up just to, I'm going to see if I can fit everything there. So you think anyone's going to watch this video? I bet they are. So if they are watching, then they could go back now and see how I did the problem and they can match up with me and they can also hit pause. So I'm going to scroll back down. So this is our last one. When you do get done, you're welcome to vocalize like what stands out to you about the answer, because there is just something that I think is different. So again, I'll start working it on the board. You're welcome to, I mean, look whenever you want. I kind of rather wait that you look when you're done and we can compare, but it's the ending that I thought was kind of interesting. So we're going to multiply the top and the bottom by 6 plus I. And the fact that the bottom is 37 is very unexciting, by the way. So that's certainly not what I'm going for here. On the top, I get 30 plus 7 is, oh, that's got to stand out, right? Well, that's interesting. And then when I do the i's, I have negative 42 plus 5, which is negative 37 i's. Yeah. Yep. So what I wanted to get at with this example is that sometimes you actually don't wind up with fractions. You just wind up with kind of more whole number a's and b's like you saw before. So when you get your fractions from here, hopefully you got this far to the big purple egg there. But when you divide this way, you don't really reduce, you just knock it down to 1. And then when you go the other way, boom, same thing. Sometimes you just get whole numbers. So you just wind up with 1 minus I like that. And it is not wrong if you put a yellow 1 like mine. It's just one of those things that people like me try to coach out of you because, oh, it's the thing. So you guys have, yeah.
Could you get like A's with the whole number?
I think you can. I don't think I see it very often, and I can't. I've done so many thousands of these, I couldn't tell you, but is it possible? I would imagine that it is. I don't see why it wouldn't be, but there's, I don't know. Good question, though. So, any questions about how to divide two complex numbers? Your assignment's on Delta Math, just FYI, and I certainly don't expect you to get it done today, okay? But I do expect you to work hard for 13 or 14 minutes. Yeah, man. Yeah.